Welcome everyone, my name is Bioprocess. I'm a chemical bioprocessing graduate. I'm going to talk to you today about the fuel consumption and performance of a single cylinder diesel engine. The project has been conducted for different reasons. Most of them is the environmental impact of the fossil fuels, and that's the driving force of most of the industries going through the biodiesel, bioenergy resources. And for that the project has been willing to use a biofuel for diesel engines, and based on the previous works, came now to a point that we need to get an instantaneous measurement of the fuel in the engine, and that brought the question: can we actually put a system that actually measures the fuel flow rate in the engine before putting any biodiesel fuel in it? So first of all, talking about the diesel engine operation, it's a single cylinder. It's a compression ignition engine, and it has a 4-stroke cycle. And by that mean, like, the first stroke is the intake, and where the actually air is going flowing through the cylinder, and then the second stroke with the piston is compressing that air and increasing the temperature by increasing the pressure. And the third stroke is the combustion, and where the fuel is actually injected into the cylinder and ignites due to the high temperature. And the fourth one, where all the gases leave when the piston goes up again and releasing that exhaust gases. So we're looking at the last point of the fuel before entering the cylinder, which is the injector. And it's very important to know how that actually works. So how that works is, as you see, the fuel is flowing through the injector from the top, and when that is supposed to be work, from that the plunger, when it gets to the combustion stroke, the plunger is lifted up by the solenoid coil, and then the high pressure fuel is injected into the cylinder. And we did the calculation for different RPMs. You see that the frequency of the injector is about 57 hertz at 1700 RPM, and that increases when it gets to 3000 RPM, where the hertz is actually 100. And the duration is very quick. It takes about 2.9 milliseconds for the 1700 RPM, and it was also decreasing when it increases the RPM. So looking at the fuel line in the system, you see it's the fuel from the fuel tank is sucked through the pump and is pressurized in this line by the pump to the injector. And matter of fact, not all the fuel is actually injected onto the cylinder. Some of it is actually going back to the tank and also from the pump. And that return line has been taken into consideration, also the high pressure, which makes it hard to implement a system on a high pressure line, and also because of the return line. Looking at the mass balance, there is opportunity to implement a system going anywhere from this side, and also that side will eliminate any return fuel from there. And looking at the input and the inlet and the outlet. So to put an inline fuel flow system, we have some requirements. One of them, that low pressure drop has to be maintained, and also practical assumption, because due to the injection frequency, it's assumed to be a continuous flow. And also there are some challenges. The engine is vibrating and block, and there is some air bubbles possibility for air bubbles trapped inside. So looking at the experiment rig, the experiment rig is implemented to find the useful power output, and we have two barrels, and the engine is this side. It's taking the water from here and also pumping it through the line and keeping that open and the other one closed, and see the fuel flowing through this loop. And the power is calculated through the pressure gauge, the pressure inside the system, and also the static pressure and the kinetic pressure due to the water flow rate, and also with the water going out. So to calculate the water flow out is to have a load cell which is connected to a data logger, and then you can see the mass flow rate of the water going out. Now to repeat it, just use the external control pump, get it back, and do the experiment again with different flow rates. So looking at the initial approach with that, first thing I did, I looked at the manufacturer data. So like the specific fuel consumption based on the manufacturer is 300 gram per kilowatt hour. And the maximum one was 2.9 gram per minute. And also then did the initial estimate experiment where we put a known amount of fuel inside the tank, and then run the engine, and then for 5 minutes, and then stop the engine, empty the tank out, and look at the difference in the fuel mass, and then how we get at different RPMs. We get a range between 1.5 and 7.1, and these two together give us like insight on how what parameters for the design should be. And also one of the important part is we have enough visual time. It should be more than 30 seconds. So we got the diameter tube 5 millimeter, and the height has to be more than 220 millimeter height. The experiment rig, the design, well, if you see it's not very clear. We have a fuel reservoir or supply from this side, and we have a few acetal cap that I made and connected with the measuring tube there. And I'm gonna explain it better in the next slide. If you see it here, you have 3 lines, and you have fuel tank, and that's the return line. So filling the tubes, filling the tank, and also it fills all the tubes here, and it has like the same height. And this line is for breathing or let the air out. And then once you see the flow is kind of smooth, then you close this valve, and then to look at the run the engine, and then to look at the fuel flow, you just close this valve, and then keep it that, and you see with the stopwatch, and you can track the fuel flow rate. And we did that at different RPMs, from 2,100 until 3,000, and you see the fuel flow rate increased from 2.8 until 5.7, and that looks very promising. And that's an average fuel flow, because the height changed when actually running that. So we want actually a quick response that gives an aligned instantaneous measurement. So we had a few options, and I'll give you some examples. But the important features about the fluid to measure for the sensors, it has to be low pressure drop, it has to be quicker response, and it has to be low in cost. So ultrasonic is very accurate, it's low pressure drop. However, it's mostly applicable for big pipelines, and also it's expensive, so that one is actually not considered. The next one we saw, I saw that the pedal is causing high pressure drop in the system, so that one is actually cancelled. And then I saw the thermal flow sensor, and it works with the 2 probes. One is measuring the temperature of the fluid inside the tube, and the other one supplying heat to the other probe. And the flow rate of the flow rate of the fluid causes heat losses from the heating element, and that heat loss makes changes to the temperature difference. And to keep that constant, more voltage or more power has to be supplied to this heating element, and that's how it works. it's low pressure drop, it's quick response because it's dealing with currents, and also it's low cost only $20. So that one was okay, and then we took it from there and we put it inside a system to calibrate it. And you see the system here. You have the fuel reservoir at the top, and we have a scale, and the sensor is in the middle here. You see this is a zoom. And to explain it further, look at the next one. So we have the fuel on the top and the sensor, and that's a flow control valve. And to calibrate it, we just open the valve and at certain flow measure the mass accumulation in the jar and calibrate that. And also the height change from that, we consider the static pressure. And looked at that, it's actually very small. It's about 0.01 millimeter, so over 1 minute. So it doesn't consider it negligible. So the calibration, did the calibration on a D100 diesel, and did it in the 50% biodiesel, 50% diesel, and also neat biodiesel at the 100. And you see the curves, looks very good, same trend. And also the biodiesels and the blend is lower than the diesel, and that's due to differences in the thermal properties of the fuels. So the sensor is measured in terms of voltage, and that's the reading, and then that's how it's calibrated. We look at the results, we run it in the engine, and you see the power output. That's the useful power output versus the fuel flow rate. And you see for difference between 1700 until 3000 RPM, the fuel consumption is quite different. From 1700 fuel consumption is low, obviously, and then the 3000 is the highest. However, there is the peak power is at one point at each one. Sometimes it's in the middle, sometimes it's in the beginning of the curve, sometimes it's in the last point of the curve, and that's due to to the engine operation and different operation settings. I also looked at the water flow rate and the power output against that. You see the 1700 to 2500 looks very similar, looks like a power pump, power curve, but that's actually not for the pump, that's for the system. For the 3000 RPM, that's different, and that's because the power is not dependent only on the water flow rate, but also depends on the pressure in the system. So closing the valve, changing the pressure, reducing the water flow rate, however, increasing the pressure in the system. And the next one, looked at the throttle settings. In the previous years, they have found that changing the pressure is actually causes some fluctuations in the throttle setting, and there was some assumption, some consideration or assumption that might be influencing the fuel consumption in the engine. However, looking at that from the 1700 or 3000 RPM, the throttle opens wider to let the amount of fuel flows more. That's expected. However, when changing the pressure in the system, the throttle setting stays the same, it doesn't change, but the fuel consumption is increasing, and that's saying that the fuel consumption is not only dependent on the throttle setting, but also dependent on the pressure inside, and pressure changes as well. And I looked at the fuel consumed per useful energy output. It's very economic when it's running on 3000 RPM. That's logarithmic. It's not very linear, but it's better than the graph that I had before. At the 3000 RPM, you see the fuel economy is very low. That means actually less fuel consumption with highest with high power output, but when running at low RPM at 1700 RPM, with the letting the engine working smoothly, is actually there's more the fuel consumed per the power output is too high, and yeah. So looking at looking at the differences between the change from RPM to RPM, you see the ratio, the increase in the power is much higher than the fuel consumption. It's almost doubled from 1700 to 2100, and for the fuel consumed, it's about 27% increase. But also, if you're looking at all, it's very much increasing the RPM. You get more power, and also the fuel consumed is actually increasing, but much less than that. So in conclusion, that we actually answering the question, yeah, I did measure the fuel in line instantaneously in the engine while operating, and also the peak power doesn't achieved, and sorry, that's a mistake. But peak power is not dependent only on the fuel consumption, but depends also on the pressure and the load in the engine. So my recommendation for that is to recalibrate the thermal flow sensor with more accurate method, for example, surge pump instead of a gravity flow, and also develop a mathematical model for that sensor for different temperature, ambient temperature, and different conditions, and for different fuels, and that gives more reliable results. Lastly, the experiment was successful in the diesel, and it's applicable to use biodiesel with the diesel at the same time and compare the differences in the results. And yeah, lastly, I would like to thank my supervisors, Clive Davis and Rose Davis. She's in Nelson. I also would like to thank Anthony and Clive Bardell for the support, and also Moyo for Coca. I didn't find his picture, but I'm sorry for that. Thank you for listening. I hope I didn't bother you too much. Any questions?
Just a general question now. When you compare biodiesel and diesel, are the density quite different? Why you say it's applicable to both? Your system.
It's applicable to both based on the thermal sensor. That when you use the thermal sensor, it picks the difference between the fuels, and also the sensor does like the change in the curve. The change in the curve indicates that the thermal differences, thermal property differences between the fuels, and that's very good. And that means actually the sensor is very good to be used for different fuels.
So, if I'm driving my car, I've got a fuel consumption in there.
Yeah.
What do they use there for that fuel consumption compared to what you've done here?
Say the question again, please.
So in a standard car, you can get fuel consumption readouts.
What are the existing methods of
measuring what's currently
fuel
out
flow
there
now?
that's being used compared to what
I looked it up, and I did struggle in that, and most of the people and the manufacturers is that the way they measure it is most of the time it's not available. But they put the fuel in the tank, they run the engine for a certain time, and then they take the difference and look at it as just the fuel consumption. It's not like specific fuel consumption or instantaneous measurement. It has been done. There is a study that was done, I came across, and he did exactly the same, and he made the system. He made the system exactly like what I did. In the same way, he put the tank, but he didn't use the sensor. He used just the height change. It's the same this one, but based on gravity flow, not like a sensor. That's the best I could ever find.
I'll put it another way. In cars, how do they measure the fuel level?
In the car?
Measure the amount of fuel in a fuel tank. Or trucks or whatever.
I'm not really sure, but I think they use like a kind of lot and measure the height change, and then there's like go a sensor. That's I know it, and that's not instantaneous measuring of the fuel. The instantaneous measurement, when you say that, is actually when the throttle changes at that certain time. I want to see the fuel change as well, fuel flow rate, the fuel consumption. That instantaneous time, but measuring that one in the car, that's an average.
Yeah, but you'll find cars do display a fuel consumption.
Yeah.
But I think you'll find it's an average.
Yeah, it's not instantaneous. It's applicable for drivers.
Why are you measuring the? What are you doing? What is the purpose of measuring the instantaneous fuel consumption?
Measuring the instantaneous, as I said, it's during the engine operation and changing the load. There are instantaneous changes inside the engine. Last year, when Clive and Rose did the experiment with the other students, they found the change in the throttle with the sensor. They put the sensor in the throttle setting, and they noticed there's a change in the throttle setting, and there was a question if that's actually affecting the fuel consumption, affecting the fuel flow rate instantaneously. So the throttle is, when you say opening, it's affecting the cross-sectional area of the fuel going through the engine. But based on the result here, when I just showed you the straight lines of the throttle, there is a slight change in that cross-sectional area. But that small change, comparing to how much amount of fuel flowing through, tells us that it's not only the throttle setting. There are some other influencing factors, and does need further study. So we achieved that we came to a point that, okay, the throttle setting is affecting, but it's not the only factor. And that's the main point. And also the system, it was meant to be run for biodiesels as well.
When you go back this can you just explain, were you opening the control valve for a fixed period of time and then closing it and then reading the weight of fuel?
Yeah.
Is that how you work?
Yeah, so that's with the stopwatch. With the stopwatch over a minute, and controlling the opening of the valve, controlling the flow of the fuel to that. And during that time, there's some reading in the sensor. And the sensor also has 30 seconds response time. So open the valve, let it for 30 seconds or 40 seconds to be sure, and then start taking the reading of the scale. So during that time, this job is not full yet. It's still running. And after that 30 seconds, start the stopwatch, look at the scale, and you see the difference in the mass of the fuel. Also during that time, the sensor also already taken readings, and we saw the standard deviation of the sensor also is very small. It's 0.00.
So are you then averaging over a minute or 2 minutes to get that grams?
That's over a minute, but that's why I said the height change, that's the reason why it has a much bigger area than this. This tube is only 4 millimeter, but this one is more than 12 centimeters.
I guess my question is, because you've got a single voltage here, is it the same voltage all the time? Is that constant, depending on how open you've got the valve?
Yeah. There is fluctuation, but if you
But
zoom it
it's,
out, it's actually a straight line.
So knowing the instantaneous fuel consumption, what benefit does that have? Like what can that be applied to? Like why do we need to know that?
We need to know that for the as I said, to enhance the interpretation of the engine performance, and that's we want like instantaneous reading. Also, as I said, for the power, for the throttle setting, during that operation, lots and lots of factors actually changing. Take an average is not enough, and that's why you need instantaneous reading at any time.
So, Mark, if you wish, I'll just make a comment. I'll ask you to make a comment just now.
Or if you've got a
Yeah, a comment or a question. I'll add a comment to Pedro's answer to your question. I think partially the animation there is very nice, but there's one bit that there is actually a free surface in the vessel on the scale. So in reality, the fluid is dripping into the container. There's no connection. There's no continuous hydrostatic head pressing on the scale. Right? And the flow rates are extremely small. As Pedro has very eloquently pointed out, the change of that height driving that fuel sensor is unmeasurable over a minute. So there's a constant flow rate. And to underscore what he said about the steadiness of the thermal sensor signal, which I thought was incredible, it's a straight line. It's an invariant number basically that goes up.
Yeah, so that's what I'm asking, because that's an average, I think, of a single point where the voltage.
Yeah, so it's bang on.
Yes.
There's no room.
Yeah, it's very.
My
That's what I'm saying.
question to Pedro would be, and you have commented a little bit on this, looking at with the knowledge that having watched you do the experiments, that data was obtained essentially in one suite of experiments. It is interesting that the B100 lies to the left of, say, the B50 and B100, and there's possibly a little bit of differentiation between the B50 and the B100. Would you have any further comment to what you've already said on the apparent? You had a question on the density in pack, and my comment would be that under the circumstances we haven't got to the point of delineating all of the thermal properties. We've started looking at that. Would you like to make any further comment? You've already commented. Here's the final opportunity just to go one step further.
Or maybe there are other factors, but as I said, I didn't look at the thermal properties because, in fact, calibrating it is very practical for this experiment. But to take it further, to develop a mathematical model, that's the time we start looking at different properties of the fuels and apply it and validate it.
Any other questions?
You can go to the next slide.
This one?
Yeah. So the curve, what the color, the gray one?
2,500,
At
yeah.
flow rate of 6, that's 2 points. Two different.
I I exactly got the same question in my mind when I saw this one. I repeated this 3 times. Exactly the 2,500 3 times, and I get every time the same result. And that's actually for the engine operation. I don't know, I'm not a mechanical engineer, but I see there is actually very interesting for this one. There are factors. There are many things mysterious still.
It's a diesel, right?
It's a diesel, yeah. It's what's running with diesel, yeah.
And what's the,
So I don't quite
what's the,
understand.
what's the, Massey fuel, what's the mixture? It's a diesel and it's injected
Yeah,
into
it's a
fuel
diesel.
and it's got air in it, so what's the ratio? What's the best ratio? Fuel?
Choose to.
So stoichiometric ratio, gives the best power output.
Yeah, it's the power is not always at exactly always in the middle. It's as I say, it's sometimes in the middle, sometimes in the left, sometimes in the right.
Are there any other questions? Otherwise, I think we will. Thank you very much.